In this lecture, we're going to talk about model specification. So model specification is the process of creating and running a structural equation model. So it's going to have 6 steps, give or take, and we're going to roughly follow this process that's shown in your Klein textbook. So the first step is going to be to specify the model. This is where you say what variables are in the model and how are they related to each other. So when you're thinking about model specification, here's some things you need to consider. You need to think about what variables are you going to include. Even if you only have a few variables in your data set, you're going to have to select them very carefully. All the concerns about normality and independence from regression still apply. You also need to think about how your constructs are measured. So you really want to make sure you have good measures that are reliable and valid. Once we get to full structural equation modeling, we'll talk about how structural equation modeling has advantages over plain regression when you're thinking about good measurement. But right now with path analysis, it's going to be the same idea. Make sure you have good measures. And the last point is related to both of the first. Depending on how many variables you have and how they're all related to each other, you might have a beautiful model, but it's not going to run. So we'll get into some details about that as we go along, so stay tuned. So while we talk about model specification, we're going to use this model as our example. The research question here is, do teachers support positive peer interactions and equal status predict interest in school? So this is using the secondary data. So you'll see it's got 818 adolescents who are aged 12 to 18. And so in general, research supports the idea that a positive school climate, when you have teachers who are supportive of you, you have interactions with your peers that are positive, and when you feel like you're being treated equally, you're going to like school more. So that's the foundation for this model. We expect positive relationships between all of these things and interest in school. All right, so when you draw a diagram like this, there's some assumptions built in that are going to affect how you specify the model in the software. So the first assumption is that all of our exogenous variables are going to be related to each other. And if you remember, our exogenous variables are variables that predict other variables. So teacher support, positive peer interactions, and equal status are exogenous variables. And what these arrows here show is that they are allowed to correlate with each other. I say allowed to because later you'll see that we can actually change this if we want. But the assumption is that they're allowed to correlate with each other. And you'll notice that this is exactly the same assumption that we have in regression. We just don't talk about it because it's just sort of, you can't change it in regression. But in the regression model, what you'll see is that you have 3 independent variables predicting 1 dependent variable. All of these are allowed to be related to each other. So you'll see sometimes these curved arrows in the diagrams, but a lot of times you won't. Even if they're not there, if these are exogenous variables, they're related to each other. Another assumption that you may or may not see in the diagram is that you're going to have an error term for your endogenous variables. And to think about this, let's go skip down to our regression equation. So when you have a regression equation like this one, interest in school has an intercept, and then you're going to have a slope for each of your 3 independent variables, and then you have an error just to capture everything that's not predicted by your independent variables. This is true in structural equation modeling as well. All of your endogenous variables are going to have an error term associated with them. In a diagram, sometimes it's not represented at all. Other times it's represented by an arrow, just like this, pointing at your endogenous variables. Sometimes it's going to be an arrow with a circle that has a little e in it to represent error terms. So you'll see different ways of representing those error terms if it's there at all. But that's some of the variations you'll see. But that's to remind you that your regression equation is always going to have an error term. And the last thing that we're assuming here is that you're estimating an intercept for your endogenous variables. So that's that beta 0 here, which is in your equation, but not going to be in the diagram. You're also estimating variances for all of these variables, for your exogenous variables and for the error term of your endogenous variable. And we'll get more into that right now. Since this is a simple regression equation, a lot of these things like the correlations, the error terms, the variances, they don't really matter that much because what we're most interested in is these slopes right here. But the more complicated our models get, the more we will care about those other aspects. So since this is a simple regression model, you can see that your equation here should look very familiar. All right, so now let's show how this model gets translated into syntax. Fortunately, it's relatively simple. You just have to remember that R and Stata are going to have slightly different ways of representing, sort of that, what the equal sign is, I guess you could say. So remember, our regression equation is interest in school being predicted by these three variables. So in R, you're going to set up a model. This is your model variable, and you're going to be putting into that variable interest, your dependent variable, and then you're going to use the tilde to say is predicted by teacher support plus positive peer plus equal, and these are the variable names right here. Okay, so R is basically going to look pretty much like the equation itself, except you don't have to tell it to, you don't have to tell any of these that you're estimating an intercept. It does that automatically. You don't have to tell it as an error. So you just need to put your dependent variable tilde is predicted by teacher support plus positive clear plus equal. And Stata is even simpler. All you're doing is interest, and this is your arrow pointing at the dependent variable, which is important, predicted by teacher support, positive, peer, and equal. So our main difference here is that in R, you're storing this in a variable called model. And so you need to have your quotation marks to just show the beginning and end of that statement. In Stata, you're putting everything inside of parentheses, and you're using the arrow to indicate the dependent variable, and there's no pluses between these variables. All right, so to show you how this can get a little more complicated when your models are more complicated, here's a mediation model with some of these same variables. So here you can see we have teacher support, positive, peer, and equal status predicting feelings of belonging, and then feelings of belonging predicting interest. So our equation for interest now, this is just two regression equations, right? So our equation for interest is literally interest and intercept, a slope for feelings of belonging, and an error term. Our equation for feelings of belonging is going to look like our equation for interest before, where feelings of belonging has an intercept being predicted by teacher support, positive, peer, and equal status, and an error term. So when we look at the syntax here, the belonging equation looks very much like the interest equation that we had before, right? Because it has three predicted variables, belonging predicted by teacher support. But now we have a second equation in here. Now interest is predicted by belonging. And that's all you need to do, because since this is a mediation model, we're assuming that everything about teacher support, positive, peer, and equal status that might be related to interest in school first predicts belonging. So belonging explains all of the variation in teacher support and interest. If you don't remember mediation, you will get to that again, but you might, if you feel a bit uncomfortable with that statement, you might want to look back at your Quant 2 notes. But let's get back to our syntax here. Again, we have our model variable that we're putting everything into, and we are enclosing this entire statement in quotation marks. In Stata, our statements are enclosed in parentheses. So our first parentheses is interest being predicted by belonging, which is before right here. And then our second parentheses is belonging being predicted by teacher support, positive peers, and equal status. So that is how we get from our diagram to our equations to our syntax. So the second step in model specification is going to be to evaluate whether or not your model is identified. So we're going to do a brief overview here and really go into detail a little bit later. All right, so in order to estimate your model, it must be identified. In order to be identified, the model must have degrees of freedom 0 or more, positive degrees of freedom, in other words. and every latent variable must have a scale. Since we're dealing with path analysis right now, we don't have any latent variables. So all we need to worry about is having more than 0 or more degrees of freedom. All right, so how do we calculate degrees of freedom? We need to understand our parameters. Parameters are numbers that indicate the size and direction of the relationship between two variables. Now, in regression, we only estimated one kind of parameter, and that was our slope. In SEM, we can estimate a lot of different parameters. We can estimate slopes, variances, covariances, and errors. On the previous slide, I was talking about how, in our current model, we don't really care about the variances, covariances, and errors because we're not estimating them. Because in regression, they're fixed. You can't change them. In SEM, we can change them, so they become parameters. So parameters have 3 states. They can be freely estimated, they can be fixed, or constrained. And we'll talk a little bit more about what the differences between each of those are. But basically, this is basically saying whether the computer needs to worry about calculating the parameter or whether you have told it what that parameter is going to be. All right, so as we talked about on the first day, we want our parameter estimates to reproduce our covariance matrix. So we want those relationships in the data to be reproduced as closely as possible. And so when we're setting up our model, that's the goal in trying to do that. Okay, so now that we know what a parameter is, now we can talk about how to estimate our degrees of freedom. The first thing we're going to estimate is the number of data points. Actually, let me start down here. Degrees of freedom is P minus Q. P is the number of data points, not the number of parameters. I know it's confusing, but that's just how it goes. So P is our number of data points. We calculate our number of data points by taking the number of observed variables, multiplying it by the number of observed variables plus 1, and then dividing by 2. This is a fairly straightforward equation. You just have to remember that K is the number of observed variables. In path analysis, all of our variables are observed. So we're going to count every single variable. Once we get the latent variables, it'll change. But right now, number of variables times number of variables plus 1 divided by 2. So Q is the number of free parameters. And this free here is really important. So in order to get Q, what you're going to do is you're going to add the number of direct effects, your variances, and your covariances. So we have this nice equation down here. And I'm going to give you an example. So we'll get into that. All right. Now, before we get to that example, we want to talk about the different degrees of freedom you can come up with. What we want to be is have positive degrees of freedom. So that means either just identified, where the degrees of freedom is 0, also called fully saturated, or to be over identified, where we have more data points than we have more parameters than we have data points. So that means our degrees of freedom are more than 0. This allows you to test hypotheses. And it's just more interesting than having a model that's fully saturated. What you don't want to have is an under-identified model where you have more degrees of freedom, where your degrees of freedom are negative. So that's going to be where you have your more parameters than you have data points. And here's another way of thinking about this and thinking about identification. So if you remember algebra, you know that when you have letters, they indicate variables that you don't have the values for. So this first example is a plus b equals 6. So you can have many different combinations of a and b in order to get to 6. You can have 3 and 3, you can have 2 and 4. So this is under-identified because you have more, you have too much information. You don't have enough information, actually. You don't have anything to limit a and b. So a and b could just be anything and you can get to 6. We don't have a way to narrow it down. When a model is just identified, that means we have just enough information to have absolutely exactly one solution. So if we know that A and B equals 6, and we know that 2A plus B equals 10, then, through the magic of solving for equations, you can get to A equals 4 and B equals 2. So 4 and 2 are the only numbers for A and B that would satisfy both of these two equations. So that's one solution just identified. If you have multiple solutions, then you get back into an over-identified situation, where once again, there are many values of A and B that could satisfy these equations. So the only way to fix this situation would be to impose some constraint on this, to say, well, okay, well, A has to be 3. So then that again makes it into a situation where you're just identified. So this is where, the amount of information, the number of data points and the number of parameters, how they get balanced into each other in identification. And you'll know, you may not remember this, but actually this does happen in regression. In regression, we have a just identified model. And the way that happens is because we're imposing a constraint. And that constraint is we minimize the squared errors. It seems really far back in there, but that is actually the constraint in how you get a just identified model in regression. So that's a kind of a hidden constraint in regression. In structural equation modeling, we bring all of the constraints into the forefront and we actually get to say what they are. All right, so even though having equations like this can be kind of frustrating in algebra, and SEM is really a way of thinking about the power that we have to identify our models. All right, so back to identification and actually calculating your degrees of freedom. We're going to go through in the first couple of weeks in class actually counting, but once you get more experience, you're not going to need to count because the software programs are going to do the counting for you, and they'll alert you most of the time if your model is not identified. Also, the more complex your models get, the harder it can be to count because you just have so many different parameters. So you'll start to get a sense for when you look at a model, whether or not it'll be identified. But I want to teach you how to count the models, just so that if you do get into a situation where the program is spitting out, your model may not be identified, you can actually go back and check and say, okay, what's going on here? Is this part identified? Is this part identified? Is that part identified? What's the actual issue? So this is a really core fundamental skill that you won't actually use that much. All right, so you're gonna get degrees of freedom from the program. If you do have degrees of freedom and are still having identification problems, there's some other things that you can check for that we'll get into more once we get into actual variables. All right, so here's how you count this example. So first, remember degrees of freedom is P minus Q. The first thing we're going to do is calculate P, and remember K is our number of observed variables. Our observed variables are anything in squares. So to support 1, positive peer interactions, 2, equal status, 3, interest in school, 4. 4 observed variables, 4 times 5 divided by 2 equals 10. So P is equal to 10 because we have 4 observed variables. All right, so that's our counting for our data points. The next thing we need to count is our parameters. So we go all the way back to our parameter equation here. It's the number of direct effects plus the number of exogenous variables plus the number of endogenous variables plus the number of covariances. And this is where your diagram assumptions are going to come into play. First, number of direct effects. These are going to be your regression slopes, so those should be pretty easy to remember. Here, let me do a different color so I can show you how this is different than our counting our data points. All right, our direct effects are teacher support predicting interest, 1, positive peer interactions predicting interest, 2, and equal status predicting interest, 3. 3 direct effects. Next, we're going to calculate the variances of our completely exogenous variables. If you remember from class, we talked about completely exogenous variables, they are all the way out here on the end, and completely endogenous variables are all the way over here. But each of these exogenous variables is going to have a variance. So that's teacher support, 1 variance, positive peer interactions, 2 variances, equal status, 3 variances. So we have 3 variances of our exogenous variables. Our endogenous variables are also going to have a variance associated, but instead of the variance being associated directly with the variable, it's associated with the error term. This is a minor point, but so if you just want to combine all your variances and say you're going to have a variance for each variable, that's fine too. So 1 variance of our endogenous variable, and then 3 covariances. If you go back to our diagram, you'll remember that we have a covariance between teacher support and positive peer, a covariance between teacher support and equal status, that's 2, and a covariance between positive peer and equal status, that's 3. So that means we have 3 direct effects, 3 variances of exogenous variables, 1 variance of the error for the endogenous variable, and 3 covariances equals 10 degrees of freedom. I mean 10 parameters. 10 minus 10 equals 0, our degrees of freedom are 0. So this model is, let me go back to you. Is it under-identified, just identified, or over-identified? It's just identified because the degrees of freedom are 0. And so here's something that you can take as, write down as a truism. All regression models are just identified. Okay? So anytime you see a model like this, it's going to be just identified, degrees of freedom equals 0. All right, whew, we got through model identification. There's a lot of counting involved just to get to 0 or just identified. But now we can move on to actually specifying the model, or actually estimating the model. So here's where client says you need to prepare your data. A lot of times we're going to be using data that's already prepared, so we won't need to worry too much about that. But you do want to think about how you're going to get your data into your program. All of the software that we're going to be using will accept text files. So that's your TXT, your CSV, comma separated, and your delimited files. So in Stata and R, you can have the variable names in the first row. Just make sure you check the appropriate box. Other file types are going to be on a case-by-case basis. So R is pretty flexible because you can import SPSS files, you can import Stata files, you can import all kinds of things. Stata is a little bit more picky, but you can generally import text files into Stata just fine. You want to think about missing data, which we'll spend the whole day on, and you want to be careful about how you have numbers and letters within the file. Sometimes Stata is a little tricky when you're importing columns, because it'll say this column is a string column, but it has numbers in it, so you have to force it to recognize those numbers. So sometimes, one easy thing that I found, if you have a text file that's having trouble getting imported, I open it in Excel, play around with it, save it as a CSV, and then it imports nice. All right, so that's some data preparation stuff. Now let's actually get to estimating the model. So what's really happening when you click run on these models? Estimation is the process of finding values that make those equations work. So there are multiple techniques you can use to estimate a model, but the default is maximum likelihood, and that's what we're going to be using until we learn about a couple other ones later on in the class. So maximum likelihood is going to produce estimates that are minimizing the square difference between the sample covariances and the researcher's models. This might sound similar to ordinary least squares regression, right? Because you're minimizing squared errors. It's actually the case. Yes, you are. Is very close. Your estimates are going to be very close to an OLS regression model, because what you're doing is essentially trying to get those squared errors to be smaller. So you're going to find that ML estimates are going to be almost exactly the same as loss regressions, especially when you have a very large sample. All right, so and also notice that this is the constraint in OLS that I mentioned. It's also a constraint in SEM. Let's see. So because what's going to happen when you're estimating these models is the program is going to just generate some numbers, right, for your for the covariance matrix. It's going to compare that to the data and say, oh, that's not good, and then it's going to re-estimate over and over and over again until it gets those differences as close as possible. So those initial estimates that it starts out with are called start values, and in general, these programs are pretty good at generating their own start values, but sometimes they have some trouble, so you'll have to provide some start values. And it's going to re-estimate and re-estimate and re-estimate until it gets to the smallest number it can, and that is called convergence when it reaches that smallest number. So some of the error messages you'll see will be about convergence. Sometimes it'll be about start values. That's what it's referring to. All right, so our main limitation in using maximum likelihood is that our endogenous variables, those dependent variables, must be continuous. We'll get to how to talk about categorical variables much later. So that's how the model gets estimated. Once you estimate the model, you'll look at model fit. Okay, so here's where we're going to kind of go over the output and what it will look like in Stata and R. So first, well, they're all going to be in different orders, but the first thing you generally look at is model fit. So we're going to get a number of numbers called fit indices. And these numbers are going to indicate the degree of correspondence between your actual data and your predicted data. Basically, how small did you minimize those errors between the model implied covariance matrix and your sample covariance matrix. So we want to use multiple measures to get to determine fit, just because each of these has their own limitations. And so generally you'll be reporting 3 to 4 or 5 different fit indices. And the client textbook will go into detail about how each of these are estimated. Right now, I'm just going to give you some general baselines for what these should look like. So some of these are going to be absolute fit, others are going to be relative fit, and all these thresholds are debatable. So try to think about your model fit holistically and not necessarily as a, okay, did it pass or did it fail? Just that's why we use multiple numbers, just to sort of give us a sense of how well are we doing. So the first model fit index that we generally look at is called the chi-square. So if your chi-square is 0, then that means your model is just identified that your model has perfectly reproduced the data. And so you want smaller numbers. You want it to be as close to 0 as possible. But chi-square has some limitations. It can be affected by non-normality. If your model is incorrectly specified and you have large correlations, then you can get a really large chi-square value. If your model is not reliable, if your variables aren't reliable, you can get some issues with that. And then the biggest problem with chi-square is that the larger your sample size gets, the larger the chi-square is going to be. And so it's basically hard to have a very good chi-square if you have a large data set, which seems like a problem because usually you want to have a big data set. So this is why people will report chi-square, but they don't really put a lot of stock into it because those bigger samples are just not going to pass the chi-square test, so to speak. So just identified model is going to have chi-square equals 0, higher values equals worst fit. So we like to use other measures besides chi-square. The first one is the RMSEA, which stands for root mean square error of approximation. Generally, you want to have a RMSEA of below 0.10. That's going to indicate good, acceptable fit, and then really good fit is below 0.05. So you want lower values. And RMSEA is going to be higher in models with smaller degrees of freedom. So this is just a limitation with that one if you just have a very, model that doesn't have a lot of free parameters. Next, we look at CFI, which is the comparative fit index. This is going to range from 0 to 1, and you want higher values above 0.9 for acceptable, above 0.95 for really good fit. And there's also a TFI, and you'll see both of those numbers reported. They're going to usually be pretty similar, but we're just going to use CFI because that's what Klein likes. And then you have your SRMR, which is a square root mean residual. I have a typo there. And higher values are going to indicate worse fit. So you're generally looking for below 0.10. So these are the 4 fit indices we're going to focus on in this class. There are a lot more. You can do a lot of reading about it if you would like, but these are generally safe ones to use. All right, so let's look at our model. So remember, our model is just identified. DF equals 0. So our fit indicators are not going to be all that interesting. Whenever DF equals 0, chi-square is going to equal 0. Since all of these numbers are based on the chi-square in some form or another, they're also going to be not very interesting. RMS equals 0, CFI equals 0, SRMR equals 0. So for a regression model in path analysis, your fit indices are not going to give you very much information because, remember, you're perfectly reproducing the sample covariances. So we'll get into fit indices in class to talk a little bit more about what they look like in a model that's not a pure regression model. But let's move on to what else you'll see in the output, which is the modification indices. So the modification indices are a way to help you determine how to make your model fit better. What it's going to do is going to tell you how much is the chi-square going to decrease if I make one change. So any modification in this index above 3.84 is going to result in a significant decrease in chi-square. That doesn't mean it's a really useful one, but at least it's significant, if you're into p-values. So generally, you're looking for your largest modification indices, and that's going to be the ones you're going to tackle first. When you look at the modification index output, you'll see a number called EPC, which is how much the parameter itself would change once you made that change. And you'll see the actual modification index itself, which is how much the chi-square is going to change. So generally, you're looking for the largest ones, you're looking for theoretically supported ones. We're going to talk about what that means more in class. Some of the limitations to using modification indices is that it might just be there's a weird correlation going on in your sample that's not represented in the population. So you might be making a change just based on what's in the sample. And also, if your model is just really messed up, these little, tiny changes based on the modification indices are not going to fix it. So for our model, we're not going to have any because it's just identified. If chi-square equals 0, there's nothing that you can't get any better than that. All right. If you do have poor fit and some modification indices that look reasonable, then you're going to re-specify the model, which basically means going all the way back to step 4 and doing all this again. But since we are pretty good right here, we don't need to re-specify. We're just going to go straight to interpreting the parameter estimates. But before I get there, I'll talk a little bit about how you re-specify them. Like I said, with modification indices, it's not going to tell you if you need major changes. You want to be guided by theory. If you have mediation models, some of the things you're going to do is look at, skipping over that mediator and going directly to a dependent variable. Sometimes you'll want to add effects between mediators. Sometimes you want to add some reciprocal effects, which basically means going back to an independent variable. Sometimes you want to remove a variable. And there's some don'ts here that we'll get more into in class. So let's skip to interpreting the parameter estimates. All right. When you're interpreting the output, it is exactly like interpreting a regression. Okay. So what we're going to do here is we're going to kind of go over some general ideas, and I'll interpret these specifically for you. So when you're looking at this column here, the coefficients, these are your regression coefficients. These are your slopes. So you're going to interpret it exactly like a slope, a change in y for each 1 unit increase in x. So this right here, teacher support, is how much does interest increase for each 1 unit in teacher support. So for every 1 unit increase in teacher support, interest is going to increase by 0.47 units. Okay, back to regression, refresh all of that. For positive peer, for every 1 unit increase in positive peer interactions, interest is going to increase 0.40 units. Equal status is a little bit different because for every 1 unit increase in equal status, interest decreases by 0.01, which is, not what you would expect, but also not significant. We're going to interpret our significance p-values over here the same way as we would in regression. So this relationship between teacher support interest is statistically significant below 0.05, positive peer below 0.05, and equal status, like I already mentioned, is not significant. So even though higher equal status is associated with lower interest, it's not the significant effect. And then you can have your intercept here. Just like in regression, your intercept is the mean of your dependent variable when all the x's are 0. Just like in regression and stata, it's going to be labeled constant. So this is the mean of interest when all of these are 0. So when teacher support is 0, when positive peer is 0, when equal status is 0, interest is going to equal 0.422. Now, if you remember back to Quant 2, your intercept is not always going to make sense. Teacher support, positive peer, and equal status are all on a 1 to 5 scale. So them equaling 0 doesn't mean anything. But that's how you interpret it, even if it doesn't make sense. Okay, next we're going to have our variance and our errors. So this is something that exists in regression, but we don't usually report it. So this is this number, let me change a different color here. This number right here is the variance in the error term for, I should have put it in red because of how we were doing our errors before. This is the variance of the error term for interest. Okay, so this number isn't usually very interesting on its own, but that's what that is. And then it's not in this output, but you can request for Stata to show you the R-square value. So just like in regression, it's going to be the amount of variance in the dependent variable, interest in this case, that's explained by your independent variables. You can also request the residual variance, which is just the inverse of the R-square, 1 minus R-square. So something that is different from regression slightly is that you can request partially standardized and standardized estimates. So right here, we have unstandardized estimates. If this was standardized, you would see the word standardized over here. And you can choose what you want to report. In SEM, we usually report the standardized estimates just because it's on a standard scale, so you can kind of, get a sense of how big each one is without having to see the standard error. But it's really your choice. It just depends on, are these variables something that, they have a natural scale like years or dollars, so you can kind of, you would get a sense for how big it was on your own, or is it something more abstract like these variables that you don't really have a sense for how big this effect is without it being standardized. So that is your option. All right, so want to say again that the estimates you're going to get from maximum likelihood are going to generally be almost exactly equivalent to what you get in regression. So this over here is your SEM output from Stata. And over here is using the Stata regress command. And what you'll see here is our slopes for interest are the same, slopes for positive here are the same, slopes for equal status are the same, a constant is the same. Okay, I told you at the beginning that we were just estimating a regression model, and that is absolutely the case here. We are just estimating a regression model. The results you're going to get from the regress command and from the SEM command, in this case, are going to be exactly the same. Now, I will say that it's the same because the process of calculating them is very similar, but not exactly the same. Once we get into more complicated models, you will see some of these numbers start to change a little bit, but I want you to keep in your mind, regression is the foundation for structural equation modeling. So that's how you get these numbers being almost exactly the same. All right, so now we're at the last step, which is where you report the results. So when we're reporting the results, usually you can do a table, like a nice regression table. Sometimes you'll go back to your diagram and you'll put your estimates in like this. So here we have our unstandardized regression estimates. Just to throw those on there, put a little star to indicate whether it's significant or not. And boom, a nice, easily interpretable figure for this, this analysis. So here we would say that higher teacher support is significantly related to higher interest in school. Positive peer interactions are positively related to interest in school, and equal status is not significantly related to interest in school. So pretty much that's how you would report this. We did get a lot of other information in this table. You'll also want to report your fit indices. Sometimes you'll talk about changes that you made to the model if you did make changes. So this is going to be your basic template. And in class, we'll get into more detail about what the standards in the field are or are not. All right, so that is the end of this lecture.